Let me introduce our group member. I'm Chu Jiesheng, and our group member are Li Junle, Carol Nisa, and Hong Jiabao. Before we get to the analogy, let's quickly review the core operating system concept at play here. Physical memory, or RAM, is strictly limited, while the programs we run often require a much larger logical memory space. To manage this bottleneck, modern operating systems rely on virtual memories. Specifically, they use a technique called demand patching. This means that a patch of data is only loaded into physical memory when a running program actively requests it. But what happens when the physical memory is completely full? If a program requests a patch that is not currently loaded, we experience what is called a patch fault because there are no empty memory frames left. The operating system is forced to solve the victim patch selection problem. It has to choose one existing patch to evict or remove to make room for a new one. This is where our two algorithms come in. They use different strategies to pick their victim. FIFO is straightforward. It evicts patch based purely on their arrival order. The oldest patch in memory is the first one kicked out. LRU, on the other hand, is historical. It analyzes recent access pattern and evicts the patch that has not been used for the longest amount of time.
To understand why picking the right victim page matters, let's look at our real world scenario. Imagine a video streaming buffer that is very small. It can only hold exactly 3 video segments at a time. Let's say a user opens a trailer, then watches an episode segment, and then watches a short clip. At this point, our buffer is completely full. Now, suppose the user immediately clicks back to ready watch the trailer. Here is where we see a FIFO failure. Under the FIFO strategy, the system looks at the buffer and says the trailer arrived first, so it must be the victim. It evicts the trailer even though the user just asked for it again. The system now has to completely reload the trailer from scratch, causing buffering and a poor user experience. This is where the LRU advantage becomes clear. LRU avoids this specific failure. It recognizes that the trailer was just requested, so it keeps the trailer in the buffer and instead evicts a segment that hasn't been watched in a while. By keeping recently accessed content, LRU significantly improves system efficiency. However, no single algorithm is perfect for every situation, and that leads directly to the objectives of this project. Through a C++ simulation, we are setting out to simulate both FIFO and LRU algorithms using predefined reference strings. Compare them directly by analyzing their page faults counts, hit counts, and overall hit ratios. Evaluate how they handle repeated access workloads, just like our users skipping back to the trailer. And finally, demonstrate a fascinating concept called Beledi's anomaly, a scenario where giving a FIFO system more memory frames actually causes it to have more page faults. By the end of this project, we will have a clear analysis of how memory utilization depends entirely on the specific access patterns of the system.
Hi everyone. For our demo part of our project, we will show you our interactive web simulation called FatFix, where we apply our OS virtual memory concept to a real-world video streaming scenario. So, in our simulator, streaming a movie is mapped directly to demand paging. The movie is broken down into a sequence of scenes. Here, each scene represents a patch in virtual memory. When a user streams the video, they request scenes in a specific order, which serves as our patch reference strings. So the physical memory assigned to the string client's buffer is mapped to patch frames, which is 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5, 6. And if a request scene is already cached in one of the buffer frames, it is a patch hit and play instantly. If the scene isn't in the buffer, it's a patch fault, which means so requiring us to fetch it from the server, causing a 0.2 second buffering delay. So let's first look at our first comparison to witness a classic OS phenomenon, Beledi abnormals. We have configured the player to compare FIFO with 3 frames on the left and FIFO with 4 frames on the right. Usually, allocating more physical memory frames should reduce the patch fault, right? Let's find out. We start streaming. Scene 1, 2, 3 are loaded, viewing the frame for both configurations. At scene 4, both algorithms experience a patch fault which is missed and must evade the oldest scene. Scene 1 to buffer scene 4, and then the 4 frames will directly to the empty buffer. Now, at step 5 and step 6, the user requests scene 1 and 2 again. So, because they were just invoked, both algorithms experience miss and have to buffer, everything the next older scene in a circular fashion. So let's move on to all of the steps. So if you finish the stream, observe the total file. The FIFA algorithm with 3 frames got 10 and 4 frames got 11. This is bloody and normal, where increasing patch frames actually increase the patch file rate, leading to more buffering interaction for the user. Next, I will hand over to Jiabao to show how we solve this using smarter algorithm, LRU.
Okay, so finally, let's look at the least recent use and the furthest first up algorithm with 4 frames. So unlike furthest first up, least recent use track which patch has been used the most recently. Okay, so when we run the same reference strings, LRU will handle the repeated access pattern much better by keeping the most recent watch segments inside the buffer. So it will finish the simulation with less faults. Okay, so I will demo it on our Flatflix. So I will choose the movie Fast and Furious. Okay, I want to watch Fast and Furious, and I choose the first file and LRU with 4 frames. Okay, so I will start the streamings. Okay, so now at the first, they will fill out the patch inside the buffer. So the first will watch the opening, tension, chest, and twist. They will fill up the buffer. So first, opening, then tensions, then chest, then twist. Okay. So now I want to rewatch the openings. Since the opening inside the first in first out algorithm buffers and also opening also inside the least recent use algorithm, so it will hit. So now you see it will hit. Okay. Then the tensions. Next, I want to watch the tensions. Since tensions is inside the first in first out and the least recent use, so it will also hit. Okay, hit. Okay. Then next, I want to watch the boss fight. So okay. So now, since the boss fight is not inside the first in first out algorithm, so first first out will replace the since one since it was loaded first, and also it was the order segment inside the buffer. Okay, so the boss fight will replace the openings. However, the least recent use is more smarter lah. It looks at the recently. Okay, since 1 and since 2 just replay for replay and access lah. So and the twist was just added, so it will replace the chest inside the buffer. So yes, so it's, as you can see, the boss fight will replace the opening inside the first in first algorithms, and the boss fight will replace the chest inside the least recent use algorithms. Okay, so next I will rewatch the opening. Okay, so in first first out, just now the boss fight was just replace the opening, so it will replace the tensions inside the buffer because the tension was the loaded second and also the order segment inside this buffer. Okay, so least recent use algorithm will hit because tension is inside the buffer. And the first in first out patch fault will increase by 1. However, the least recent use will not increase by 1. Okay, so yeah, as you can see, this first fault hit miss, and this least recent use is hit. So tensions least recent use hits, and first fault will replaced by the chest. Okay, then next is chest. First file replace the twist, and this algorithm will replaced by the segment which just now didn't access. Okay, the so twist boss fight credits. So as you can see, the least recent use algorithm have only 9 patch faults, but first in first have 11 patch faults. So this clearly demonstrates that the least recent use is more efficient for this type of workloads because it accounts for temporary locality. So the idea that if I watched a scene recently, I will likely to watch it again soon. So to conclude, our project showed that the choice of replayment algorithm is important for the system response. While FinFET is easy to implement, it's prone to delay anomalies and perform poorly with the repetitive data. However, LRView are more context away, provide a smoother streaming experience. So thank you very much for watching this video.